Yes, we want to say some things relating to the rate of lexical change. Now, why is it interesting to know anything about the rate of lexical change? Well, if it is constant, it means that we can simply calculate the time at which two related languages diverged. This is called glottochronology, the idea that it happens at a constant rate. And this formula is already from the 50s. All you need to know is for two languages what their cognate density is, namely how much a percent of their vocabulary is cognate. And then you plug that into that formula, and out you get the calibrated number of years for this split. And here's an example. So you have English and Swedish, and some words look a little bit different, but they're just phonetic changes. They're really the same word, so they're cognates. In other cases, you have a word like, for the meaning bird, you have fågel and bird, which are totally different words, so they're not cognate. And the cognate density for Swedish and English on a 200-word fixed list is 60.5%, and that gives you 1192 years. Excellent, fantastic. However, there has been a lot of criticism about the constant rate of change hypothesis and criticism about glottochronology. There's a lot to read, but there's two more important papers. The first one takes historically attested languages and then just simply compares the rate to the modern languages. So he's got 3 cases and then finds that the rate isn't exactly constant. The second one doesn't actually look at historically attested languages, but looks at a whole big subfamily of 200 languages, reconstructs their proto-language, so that's not attested, but he reconstructs it, and then he can simply check for every modern language how much they retain. And as you can see, out of 200 languages, there's an incredible variation. Some languages retain 58% and others 5%, so it cannot be constant. But there's something fishy here, namely that, for example, if you look at the language that retains the most vocabulary from Proto-Malayo-Polynesian happens to be Malay. Malay also happens to be the most well-known Malayo-Polynesian language. It's quite a coincidence that also happened to be the one that retains the most. Maybe what really happened is what's known as Teeter's law, that the proto-language tends to look like the language, the most well-known modern language. So maybe Blust in his reconstruction had some sort of bias towards Malay, and we can't really take these numbers at face value. In the modern era, now we have much bigger lexical databases, and it's what seems to be the best case, namely historically attested data versus modern language, perhaps isn't actually the best test case, because it's not so easy to get a snapshot of a particular date and the exact base vocabulary for a historically attested language. Usually if you pick up a dictionary of Old Egyptian or Old Greek, they give you everything that happened in a time span of 1,000 years and every word that's related to such and such meaning. Or care, or stay away from it at all. And then if you stay away from it at all, you have this other option that you look at modern languages, you try to reconstruct the proto-language, and then you check the retention. And then what you want to do is, you don't want to fall into the same trap as Blust, that there is some hidden human bias there, but you also want to do it with computers. But then you get into very intricate questions about inferring the tree, checking the proto-stage, and the change rates, which Philip will go more into.
Yeah, so one thing which is quite a problem, or it can change the results a lot, is like which model of vocabulary evolution you use. And this is basically true for every method. You need to assume some model of how words evolve along the language tree. Yeah, and so first of all, those models you can use, they depend on the way you code the data. And most often you use binary data coding, which basically means, so if we have word lists, say a Swedish list, and different meanings in languages. So here we have the meaning to and the meaning dog in English, German, and Spanish. Then first what you use, you code them for cognacy. So in this case, we see that English, German, and Spanish, well, those words are basically the same, minus sound changes, so they are cognate, while dog, hund, and perro, those are really different words, so they are not cognate. And then when you code the data, what you do is for every Well, words which are cognate to each other, they will be put in the same cognate class. So in this case, you make one class for the word, for the meaning to, where all English, German, and Spanish inhabit this class. And then for the meaning dog, you make actually 3 classes, and which is only inhabited by one language at a time. So you can code the data by zeros and ones, basically. Yeah, first you extract the number of classes, and then you code it by zeros and ones. Yeah, so if you have this data coding, and now you want to see what happens in a given language tree, well, the thing is you need to specify in some way, like how zeros can change into ones, and ones into zeros. So this basically means, well, when a cognate can be lost in language and when it is gained, and you have to make some theoretical assumptions there. Yeah, and well, there are different models which are used for this binary coding. Well, the maybe easiest one is continuous Markov change. This basically says that cognates, so new words, can always, along a given language tree, be born in a language, and there's a certain probability that this happens, and they can always die. So you do not really make any restrictions. While in Stochastic Dollar, which is another model, you say that a cognate can only be born once in a tree, and then it can survive down to the tips, or it may not. So this basically means that in 2 different branches in the tree, you assume that it is impossible that the same word, the same like cognate words, will evolve at 2 times. So you assume every new lexeme can only evolve once in the tree. Yeah, and then there are some other models, like covariant and pseudo-dollar. Yeah, so what is like the problem with this coding and those models? Well, we think a problem is that proto-languages are allowed to have a lot of words for the same meaning in this model. So, well, in this example, like all those models allow for the possibility that our proto-language well had a 1 at every position. In this case, it means, okay, it had the cognate class for the meaning to, but also it had all the meaning classes for the meaning of dog. So it would have perro, hund, and dog, all of those words. And in principle, this is of course possible, but if you have a lot of languages and a lot of meanings, you can get situations where say the proto-language has 10 different words for a certain meaning, and this is kind of implausible, and because most languages only have 1 or 2 frequently used words per meaning. And we think that there's skews the results in the models used. It's kind of intricate in which way this happens, and we haven't quite figured it out, but we think it at least has some effect on what tree topologies and what branch lengths are constructed. Yeah. Okay, and well, our proposed solution is a model which allows every language to have only 1 word per meaning. And this is possible with MultiState models. So they assume not binary but MultiState coding, which works as follows. So if you're here again, we have our 2 meanings, which are coded for cognates. And then if we do MultiState coding, we basically do 1 coding for every meaning, for every language. So for the meaning to, English, German, and Spanish, they get the same number. And for the meaning dog, they get all different numbers because they have all non-cognate words. So you code, instead of zeros and ones, you code by natural numbers for every meaning. Yes, and then, well, there are also different multi-state models possible, but the model we are working on works as follows. So moving down the trees, meaning states can change with a certain rate, and if a meaning state changes, it will always change into something new, which has not occurred in the tree before. So a bit like Stochastic Dollar, we assume that new words can only appear once in the tree. Here's a visualization for one meaning. Say we have one meaning, which we give some number, and then we proceed down the tree. Then it is possible that a daughter of this language will either retain the meaning or innovate a new one. So in this case, this daughter retains it. Here we innovate a new one, and then again here this language retains the meaning, and here we innovate a new meaning. Sorry, not meanings, words. I mean, innovates new words for the meaning. Sorry, that was confusing. But the important thing about the model is this is a 3 and not a 2. So it is impossible that like the 2 involves at 2 branches in the tree. And the advantage of the model is that, well, it's linguistically more realistic that a word can only be born once in the tree, and by fixing one state per language, per meaning, by using this multi-state model, we will not run into troubles of proto-languages being able to have a lot of synonyms. So now, for being able to use our model like efficiently to find which tree topology or which branch lengths fit the data well, we must be able to calculate likelihoods. So we must, given a certain tree, we must be able to calculate the likelihood that this tree has produced a certain data set. And this, in principle, is a difficult thing. It is like exponential in complexity, but we were able to find an algorithm which is not exponential. I think it's even linear, but it works pretty fast. And and so the basic idea of this algorithm is, I will only sketch it. It's very hard to explain, but so the idea is that if we have a given data set, and now we look at only one meaning, so in practice you would do that one meaning at a time. You would look what the words for your given meaning are in the different languages, and then you calculate probabilities. So in this example, we have like 7 languages, and we assume all of them have, well, this is like made up data. We assume that all of them have like different words for the meaning, except 2 which have the same. So the first thing we do when calculating the likelihood that this tree produced this data is we fill out some internal values. Namely, because our model assumes that it is impossible that the same word will appear 2 times at different branches independently, it must, because here we have 2 ones, they must come down from the common ancestor. So they must have appeared here, and then they actually must also have survived here. So this we know. But then there are also other things which the data tells us, and this information will affect the likelihood of the tree. And these other things are basically, well, which data is different. So here we had like equalities. We knew that 2 languages had the same word, but in other cases we know that languages have different words. But this will also affect the likelihood because, for example, here where we have the 5 and the 6, we know that the common ancestor must have changed meaning at least once. So either along this branch or at least this branch, the meaning must have changed because otherwise they couldn't be different. So, and this will affect the likelihood. It will make it a little bit lower because we know that a change has taken place. So the possibility that here's no change must be excluded. And if you go further up the tree, it gets a bit more intricate. Like you still will get information from the data you have in the tips. But our algorithm is able to to calculate the true likelihood. Great, I think we're pretty good on time, which is good, because then we have a lot of time for questions.